So if we have two vectors, u and v, we might want to figure out what the angle is between them, because that can be useful when we think about physical quantities and how these vectors kind of relate to one another in not only a mathematical sense, but in a lot of ways a physical sense. So if we want to figure out how these angles are related to each other, then we can use the dot product to say that the value of the dot product is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. And this is often useful when you only know the magnitude and you only know the angles between the vectors. This is going to be common when you think about what we did when we did the word problem in the previous section, where we knew the force that was acting upon it and we knew the angle that it was coming at. We could have used something like this to solve that problem a little more quickly than the way we did it. So that's very useful if you know these magnitudes and the angle. But often, especially in the type of class we have, you're not going to know that. You're usually going to know what the value of the components is. So if we want to figure out what that angle is, we can take the dot product, which we can compute from, we already did, and then we can find the magnitudes, which we already know how to do, and we know that cosine of theta is equal to those. Now, I'm not going to prove this, but a proof of this is based upon the idea of the law of cosines. So I don't remember if you remember from geometry, the law of cosines is kind of a generalization of the Pythagorean theorem. It's the a squared plus b squared equals c squared, but you have that minus 2ab cosine theta in there. And that ultimately tells you a little bit about what you're dealing with, and you would use this vector here. So if you want to look that up, that's just to kind of satisfy your own curiosity. That's there. I want to point out, though, that when we talk about vectors, that the inverse cosine has a range of 0 pi. What does that mean? Well, that means that if you take the inverse cosine of both sides of this, you're only going to get a value in 0 pi. You're never going to get like a 3 pi over 2 for theta here because of the way the inverse cosine works. So what you're really getting is the shortest path, because you could theoretically use that. You could use this angle, which is pi minus theta, and that angle would still satisfy all these equalities here. Or 2 pi minus theta, I apologize. So anyway, that's just something to note, that if you use this formula to get the angle, or if you know the angle, but then you use these formulas, you might recover a different angle than you started with. Anyway, I want to talk to you a little bit about this idea of orthogonality. So if I have two vectors and their dot product is 0, then we say that u and v are orthogonal. Well, think like perpendicular. If I have two vectors that cross at a right angle, if I go back to here, if they cross at a right angle, cosine of theta would be cosine of pi over 2. Well, cosine of pi over 2 is 0. So u dot v is going to be 0. So it works both ways. So what we know is that if we have u dot v equals 0, the angle between them is pi over 2. We also know if the angle is pi over 2, u dot v will be equal to 0. Orthogonality is a huge component in linear algebra, and in a real world sense, a lot of times you want vectors to be orthogonal because when you want to move in directions, you want to make sure that the directions you choose are never going to interact with each other in a specific way. Think like your I, J, and K vectors. Those cross at a right angle. So if you're moving along the x-axis, you're never moving slightly along the y-axis or anything like that. So orthogonality is very, very big. But that's it for the angle between vectors.